Okay, let's continue. We're going to finish the last theorem, the theorem 4.30. Okay, the theorem 4.30. It is an intermediate value theorem, but for the derivative. We know the intermediate value theorem for the continuous function. You have a value between fa and fb, then if it is continuous, like this, the m is here, then this horizontal m will intersect the graph. So this is an intermediate value theorem for the continuous function. And this theorem 4.30 is called intermediate value theorem for derivatives. Okay, intermediate value theorem for derivatives. Okay, now let's see, suppose that f is differentiable on the closed interval AB with f prime of A is not equal to f prime of B. Alright? Okay. If y0 is a real number that lies between f prime of A and f prime of B, then there is an x0 in the open interval AB such that f prime of x0 is equal to y0, Okay, so the important or the difference between the intermediate value theorem for the continuous function and this theorem is that we assume f to be differentiable. Of course, f itself is continuous, but we do not assume f prime to be continuous. Okay, we have f continuous, but f prime may not be continuous. Even though f prime is not continuous, we still have this intermediate value theorem. So that's the difference. That's the difference. If f prime is continuous, this is just the corollary, the application of the regular intermediate value theorem. Okay, now let's see the proof. The proof is not long. Let's see the proof. So assume that y0 is between f prime of A and f prime of B. Well, here you have f prime of A not equal to f prime of B. Then either f prime of A is less than f prime of B or the other way. And when this happens, you have this one. And symmetrically, you have the other case. Symmetrically, you will have the other case. Okay? So, by symmetry. Or you can just say without loss of generality, let's assume this is correct. Okay, and be careful, this rest of the computation will depend on this assumption. Okay, let's see. Let capital F of x be little fx minus y0 times x. Okay, capital F of x is y0 is equal to fx minus y0 times fx. Okay. Okay, and then for x inside the closed interval a and b. All right, and of course this capital F of x is differentiable capital Fx is differentiable on the interval AB. Then differentiable is continuous, right? Differentiable function is of course continuous. Then by the extreme value theorem, capital Fx will have absolute max and absolute mean. By the extreme value theorem, capital Fx has an absolute maximum value and absolute minimum value. Okay, extreme value theorem. Now let's talk about this absolute mean. We will see why we select absolute mean, not absolute max. Okay, we will see that. Okay, so we're going to talk about this absolute mean. Say capital F of x prime is an absolute mean. Absolute minimum on the closed interval AB. Okay. Well, absolute minimum value. Let's check f prime of a. F prime of a, we just do the differentiation, is f prime of a minus y0. F prime of a, it's a decreasing. It's decreasing, right? So let's check what is the meaning of a. Sorry, it's a negative. It's negative. What's the meaning of it? A here. If you have a function, the derivative is like this at the point A. And the derivative is like this at point A. So what is the derivative? Derivative remember this is the left end point, so we have to assume h approaches from right hand side. Okay. This limit is negative, so eventually when h is sufficiently small, the whole ratio will be negative, right? So when h is sufficiently small, the ratio is going to be less than 0. Right? The ratio is going to be less than 0. And h is positive, then it implies the difference is going to be negative. The difference is negative, then fa is greater than f of a plus h for all the h in some small interval. So f of a cannot be what? Cannot be the minimum. Right? It's greater than f of a plus h, so it cannot be minimum. It cannot be the minimum, so what we get? We get x0 is not is not equal to a. X0 is not equal to a. Alright, so this is a case x0 cannot be a. It cannot be this endpoint. Let's check the other part. F prime of b. F prime of b is f prime, little f prime of b minus y0. Okay, and this, what's this? This is greater than 0. Why? The greater than 0, less than 0, they both come from this relation. They both come from this relation. Okay, and then similarly, so f prime of b is equal to this limit h approaches 0 from left hand side, right? Okay, and what is this? Okay, it's a greater than 0, but h approaches 0. And this is the right hand side. This increment has to be negative. So for h is sufficiently small and negative, this ratio should be positive. B plus h minus f of b over h, it should be positive because eventually the limit is positive. It's like the sign preserving property. Okay, the denominator is negative, so you still get f of b plus h minus f of b to be negative. Okay, and this implies fb is greater than fb plus h. So fb cannot be the absolute minimum. It's not even a local minimum. Okay, so this implies x0 is not equal to b. X0 is not equal to a, x0 is not equal to b. X0 belongs to the this is open interval AB. If it belongs to the open interval AB, we know that how can, for a differentiable function, if it achieves a local extreme value, I mean here's absolute, now it's an inside the interval, then f prime of a must f prime of x must be equal to 0. It's called the critical point, right? Critical number is called the critical number. When we say that the critical number means either f prime of x is 0 or f prime of x does not exist, and plus the endpoint, they are the candidate for the continuous function to achieve the absolute extreme values, right? Okay, so f prime of x0 is equal to 0, and then this is equivalent to say f prime of x0 is equal to y0. The difference, where's here? The difference is 0, so they equal to each other. See, it's a very, very delicate proof. It's very good. It's very, very, very good. Okay, so that's how the complete proof. The proof ends. And now let's go back to the question I proposed. So here we assume y f prime of a, f prime of b in such order, and then we choose absolute minimum value. Just because at this point you do not have x0 equal to a, x0 is equal to b. Assume you choose absolute maximum value. If this place you choose absolute maximum value, you will get f, the whole thing will not change, but you will get f of a is greater than f of a plus h. then you don't have a contradiction. Fb is greater than Fb plus h, you don't have a contradiction. Okay, so these two parts do not change. Then these two conditions will not contradict to the maximum value. They will only contradict to the minimum value. Okay, so that's why this place we can only select absolute mean, not absolute max. This place there's no symmetry. But what is a symmetry? Symmetry is the following. This is end. This is end. This is a remark. If in the proof we assume that f prime of A is greater than y0, greater than f prime of B. If we assume the other case, then we should consider f of x0 to be an absolute maximum. Okay, so if you have this situation, you change the direction of inequality, then you're going to see the absolute maximum. You will see the absolute maximum. That will give you the contradiction. The reason is that you still do the same argument. So you will have f prime of A, which is f prime of A minus y0. This time is greater than 0. This time is greater than 0. Then you will get f of A plus h minus f of A greater than 0 for h greater than 0. Then you will have f of A plus h is greater than f of A. So f of A cannot be the maximum value. And similarly, f prime of a B is equal to f prime of B minus y of 0. It's less than 0, but f of B plus h, you just copy it here, minus f of B, this place is going to be, here's negative, so this is going to be positive for h negative, because here, be careful, this h is negative. The numerator is negative, the ratio is positive. Here h is negative, numerator is positive, the ratio is negative. Okay, so f of B plus h is going to be greater than f of B. So FB both cannot be the maximum value. Okay, so in this setting, you are going to consider the absolute maximum value. In the setting in the textbook, you're going to consider absolute minimum value. That's a symmetry. That is the symmetry. Okay? Okay, so this totally finished the chapter 4. And this proof is very short, very good, very proper for the exam. Okay, so you're going to check and memorize this proof. Okay, now we finished the chapter 4. Now let's talk about chapter 5. Chapter 5 is integrability. On R, we're going to do the integration. We just do the differentiation all the time. Okay, so Riemann integral. The Riemann integral. The Riemann integral comes from the Riemann sum. Riemann sum comes from the partition. Okay, so let A be in R with A less than B. See, a partition of AB interval is a set of points P is x0, x1, xn. Here, remember this place there's n plus 1 point. Okay, n plus 1 point, such that A is equal to x0 less than x1 less than x2 less than less than xn is equal to B. Okay, so you will have A and B. This is x0, this is xn, 1, 2, xn minus 1. So you have n plus 1 points. You have n plus 1 points. This is called the partition. And 2, the norm of a partition P equal to x0, x1, xn. The norm is the number. We use norm P equal to the maximum of ops value xj minus 1. Here j is from 1 to n. What is a norm? Remember here you have n plus 1 points, and you have n intervals, subintervals, n subintervals. For those n subintervals, you measure the length of each one. You measure the length. The ops value of the difference gave us the length. The ops value of the difference gave us the length. You measure the length of the intervals, and you pick up the largest, the longest, or the largest length. You pick up the largest length because you only have n subintervals. There's a finitely many number. So you pick up the largest length. That is called the norm. Okay, that is called the norm. 3, a refinement of a partition P x0, x1, xn is a partition Q of AB that satisfies Q contains P as a set, Q contains P. Okay, so then Q is called a refinement, like a superset. Q is called a refinement of P, and we say that Q is finer than P. Q is finer than P. Okay, so basically what is a refinement? x0, xn, x1, xn minus 1, x2. Refinement means you first have a P and you just add a bunch of points. Just add other points into this partition, and you chop this subintervals into even subintervals. Okay, that is a refinement. Okay. Okay, so partition is a very, very broad definition. You can define like this, or you can define like this. 1, 2, 3. Like you always keep x0, x1 very long. And all other points are just squeezed together between x1 and xn. That's possible. So partition does not require all the points should be scattered. But for this partition, its norm is like this. The norm is not going to be small. Okay? So that's a partition. Let's see the example. Of course, when we imagine a partition, we always say, let's chop this interval. We cut interval into small subintervals. So how do we guarantee it is small? We have a technical partition. It's a dyadic partition. Dyadic partition is the following. So we have Pn equal to j over 2 to n, where j is from 0, 1, 2 up to 2 to n power. Okay, so we have P sub n to be a partition like this. And then P sub n is a partition of 0, 1, and Pm is finer than Pn if m is greater than n. Pm is finer than Pn if m is greater than n. Of course, it is a partition of 0, 1. When j is 0, this is 0. When j is 2 to nth power is a 1. So this is not difficult part. And there's no difficult part. And Pm is finer than Pn. Let's check this. We will understand. What is P1? P1 P1 n is equal to 1, so it's a 0, 1, 2. 0, 1, 1 is here, and 2. This is 0 over 2, 1 over 2. This is 2 over 2. Just divide the interval equally into two parts. And the P2 is 0 over 2 squared, 1 over 2 squared, 2 over 2 squared, 3 over 2 squared, 4 over 2 squared, square. Right? So basically, you always divide interval into two parts. Every time you divide the previous partition into two parts. So of course, when Pm is greater than n, it is going to be finer than the previous partitions. Right? So this is a dyadic partition. It is a good partition. All right. So that's an example dyadic partition. And when we have two partitions, in general, if we have two partitions, P and Q, in general, they have no relation. Here, relation means which one is the one is finer than the other one. So for arbitrary two partitions, you cannot always get one is finer than the other one. That's impossible. But if we put, you remember this is sets. There are two sets. If you get the union of two sets, union about sets, if they are repeated, you just keep one copy, right? But this union is always finer than P and Q. Be careful here, finer. P itself is finer than itself. Here we allow equality. So P is finer than itself. We allow equality. P is finer than itself. Okay, so this is one observation. If you have two partitions, of course, about the same interval. If the different interval, there's nothing you need to discuss. Okay, for the same fixed interval, you have two partitions. You put them together, get a union. It is going to be finer than both partitions. And for a finer partition, we can see that the norm is going to be decreasing. The norm of the finer partition is less than or equal to the partition of P, right? So the finer partition will have non-increasing norm. The norm does not increase when you add more points. Actually, it decreases, right? It decreases. Okay, so now let's review the idea of the Riemann sum. And actually here is not a Riemann sum, but it's close to the Riemann sum. We're talking about a Riemann sum starts from the computation of area. Area, of course, this moment we always talk about positive function. Let f be non-negative. On the interval AB. And then you have a partition. x1, x2, x3, x4. Of course, we also want f to be bounded. We don't want it go to infinity. We start from the good case, not the improper case. Okay, Riemann sum says when you have a partition, you're going to pick up arbitrary sample point from each subinterval and measure the height, and then do the product with the base times height is the area of the volume, area of the rectangle, and then you add them together. Arbitrary sample point. But here we are going to study another version of a Riemann sum. Another version. We do not randomly pick up a sample point. We are going to always choose some special version, special values. That's okay. So let AB be in R with A less than B. Let P be x0, xn be a partition of AB. It's a partition. And suppose that f from AB to R is bounded. To be bounded. And then we first the upper Riemann sum of f over p is what? Let me see. U F P is equal to, remember we're going to have a Riemann sum. Riemann sum is a height times the base. Height, this place, F is bounded. Bounded, of course, over each interval is also bounded. Bounded, you have a maximum and minimum, or you have a supremum, not maximum, minimum. If continuous, you will have maximum. Here you have a supremum and infimum. Bounded function will have finite supremum and finite infimum. So for each interval, we are looking for the supremum over that subinterval. This is supremum over the jth interval. This is a first, and this is a second. This is a third, and a fourth, fifth, right? So you have a jth interval, and you measure the supremum over that interval, and xj minus 1, that is the base, the length of the base of an interval. Okay. And then you add them together from 1 to n. Remember, you only have n subintervals. You have n subintervals, you will have n rectangles. This is upper Riemann sum, where mj of f is defined to be the supremum of fx, where x belongs to xj minus 1 and xj. And yeah, that's it. Okay, so you do not just randomly pick up a sample point and measure the height. You choose the supremum. You choose the supremum. This is a upper Riemann sum. Of course, you can choose the supremum. You can also choose the infimum. The version for the infimum is called the lower Riemann sum. Of f over p is L f p sigma little mj of f xj minus 1. This is always a base. This is always a height. J is from 1 to n, where little mj of f is the infimum of fx. X belongs to xj minus 1, xj. Right? This is the supremum, infimum, and then you define the upper Riemann sum and the lower Riemann sum. Upper Riemann sum and the lower Riemann sum. Okay. So these two are the similar definition like the Riemann sum, but just special one. So that's why we just still use the Riemann sum, but we gave a name. And now let's check the an example. So assume we have fx to be the constant. Fx is alpha, a constant. On AB. Assume it's a constant function. Then let's check what is the upper sum. Upper sum, this time a constant function, the supremum is just itself, it's just alpha. And then you are going to add all those differences. Those differences are just intervals, the length of subintervals. You add the length of those intervals together, you will have the length of AB. Okay, so the upper sum is alpha times b minus a. And if you do the computation for the lower sum, you will have the same thing, because the lower sum, the infimum is also alpha, and then you still use the sum of all the lengths of subintervals, which is equal to the length of the total interval, b minus a. And this type of thing in the book, they use another remark. They call it telescope. Okay, the telescope. You have a step. You have basically telescope is like this. G0, G1, G1, G2, G2, G3, until Gn minus 1 and Gn. You can compute the, once they have such order, you can compute the difference between G0 and Gn, or you can compute G0 to G1, G1 to G2, G2 to G3, G3 to G4, and Gn minus 1 to Gn. And you compute all the differences step by step, and you add all the differences together. If you add all the differences together, don't miss any term. If you add all the differences together, it will be the whole difference. Okay, so that's a telescope. It's called the telescope sum. But here's a telescope sum. And if you have a constant function, the upper Riemann sum and the lower Riemann sum both equal to alpha times b minus a. Both equal to alpha times b minus a. All right. Okay. Another remark. We have lower sum, we have upper sum, and we know that the lower sum is always less than or equal to the upper sum for all partitions. P and all bounded functions f. Here, when we draw it, I always draw the graph of the function above x-axis, because in this case, we can talk about the area below the graph. But the lower sum, upper sum, the Riemann sum, the general definition here is especially for this one. The general definition only requires a function to be bounded. It can be above the x-axis, can be below the x-axis. It's not always positive. Okay, so we say non-negative. We just want to say that is the origin of the idea, or the origin of the Riemann integral. They want to use the Riemann integral to compute the area of the region. In that case, you have to be non-negative. But when we discuss the general Riemann sum, or this upper-lower Riemann sum, we don't need it to be non-negative. Okay? This is just for the origin purpose. It's not for the definition. So f could be negative in this case. And for whatever partition P and whatever bounded function f, we always have the lower sum fp is less than or equal to the upper sum fp. Lower sum fp is always less than or equal to the upper sum fp. F and p are the same. This simply because the infimum is always less than or equal to the supremum. And then you also multiply the inequality by a positive number. Xj minus xj minus 1 is positive, so you have this. Okay, so that's not a big deal. Okay. Now let's see a remark one step further. Here, P is the same P. lower sum fp is less than or equal to the upper sum fp. Now let's see if p is any partition of AB, and we have a refinement. Q is a refinement. Of P. Then, of course, F is bounded. F is always bounded in this case. Then the lower sum of Fp is less than or equal to the lower sum of Fq, less than or equal to the upper sum Fq, less than or equal to the upper sum Fp. So we see that the lower sum is increasing function when you with respect to the refinement, but the upper sum is decreasing function with respect to the refinement. Okay? So this is a increasing, this is a decreasing for whatever refinement. The proof is not difficult. So assume refinement, you can have 1, 2, 3 more points. Let's just assume Q is P union X, not X0, X prime, and X prime is between Xj minus 1 and Xj. Okay, so you just add, assume you just add 1 point, and then you can continue to add more and more and more. You always have such property. All right, so and then that's by the induction. Now let's see this J0. Then the L of Fp is mjf xj minus xj minus 1. And we break it. Those j is not equal to j0. We have such stuff. For j equal to j0, we have mj xj0, and then we put minus x prime plus x prime minus xj0 minus 1. So here is still the equality. Okay, here is still the equality. And then copy the first part. Okay, so basically you have this xj0 minus 1, xj0, and you break it. You break it into two parts. And for each subinterval, the infimum may not be the same for f, but the infimum is always increasing when you shrink the interval. So let's say this is a, let's use, it's increase, infimum is increasing, so it's less than or equal to the first part. Let's call it mj 0 prime of f, then xj0 minus x prime, and plus mj x0 double prime of f, x prime minus xj0 minus 1. Here mj0 prime is infimum over the first part, first subinterval. mj0 double prime is interval is an infimum over the second subinterval, and this is equal to the lower sum of fq. So we do prove this. Okay, here we use that mj, the infimum is increasing when you shrink the domain. You shrink the domain, the infimum is increasing. And this part is done. This is the previous remark. And u is decreasing. This whole thing comes from the supremum is decreasing when you shrink the domain. Right? Supremum depend on the larger domain. The supremum will be bigger if you have a larger domain. So supremum is decreasing when you change all the little mj into the capital MJ, then you have to change it to be greater than or equal to. So that's why Q will be less than or equal to the P version. UFQ will be less than the UFP, and that is the second part. Alright, so if you have a refinement, then you will see that the lower Riemann sum is increasing and the upper Riemann sum is decreasing. Alright, so that's a proof. You can finish this whole proof completely by yourself. Okay, so we'll finish the video at this moment and we will continue in the next video. Thank you.